Thank you. Thank you very much for the invite to come down here, and thanks for such a warm and glowing introduction. I wish my colleagues were half as good at giving introductions as you are. That's awesome. And now I feel quite bashful. So, what I'm talking about tonight is rocks from space. I'm talking about the potential for objects to crash into the Earth, do things like this, and cause us problems. I mean, this will clearly not be a good day if you were down here. I don't, unfortunately, have any rocks from space with me. I don't have any meteorites with me. But at some point, may try and look at getting some in the future and to be able to bring them down. That's something we'll have to work on in the future. But you can get access to these things. There are probably some in the museums in Sydney. I don't know for certain, because I've not been, but you might be able to handle some there. I've been asked by Fred to mention as well the worksheets. There are worksheets out in front of you that you can fill in through the evening, hand them in to Fred at the end, and you'll get a prize. The person who does best can get a prize. So that's another reason to keep listening to me. I've got plenty of real nice pretty pictures, hopefully got an interesting story to tell you. Where I'm going to start that story is an event that happened just over a year ago over a town called Chelyabinsk. So that's where I'm going to start to give us a bit of an introduction. I'll move on from that to tell you about our solar system, and in particular the small objects in our solar system, the things that can actually threaten us. I'll break that down and tell you the current fairy tale, the story we have about how our solar system works, how our solar system formed, and tell you where the potentially dangerous objects come from and how they get here. I'll then give you a brief overview of the history of collisions with the Earth, from ancient history to the modern day, and then talk about the modern impacts, before finishing off with a little bit of a discussion of the future, some time for questions, and also an advert of something that you can look out for in the sky yourselves next Wednesday evening. So a bit of something for everybody. But this is where we start, this incredible photograph. Chelyabinsk, a city in Russia, a city I'd not heard of, most people hadn't heard of, despite the fact that it's a fairly hefty city, over 1 million people, somewhere out in the depths of Russia. This is February last year, but because it's the Northern Hemisphere, that means it's coming to the end of winter. At 9:20 in the morning, it's still dusk. The sun's only just rising. You're way up near the Arctic Circle. As you can see here, it's only just getting daylight. And what happened was this. I'll let this video run as I talk to you. One of the really cool things at the minute, although probably not for a great reason, is that in Russia, people drive around with GoPro cameras on the dashboards. And occasionally they see things like this. So the first thing that astonishes me about this video is that the guy sees this and carries on driving. Right? I'd be panicking. But the prevalence of these cameras on car dashboards was astonishing. It's such a great resource for scientists. This is just a bit slowed down. What you're seeing here is something, and I'll go into the details of this a bit more in a moment, hitting the Earth's atmosphere, a large rock from space. Travelling into the Earth's atmosphere at a speed so fast that it will cross Sydney in seconds. Really high speed, which means it's carrying a lot of energy. And as it hits the atmosphere, it causes the air in front of it to heat up, and it causes the thing to start to ablate, to burn away into the atmosphere. And as it gets deeper and deeper into the atmosphere, it burns more brightly and more vividly until it reaches a certain height, and in the case of this rock, it explodes. It's what we get here, a big detonation. These kind of things happen all the time. Okay, not so spectacular as this, but any night of the year, step out, and if you watch the sky and it's clear for a certain amount of time, you'll see a shooting star. This is like a shooting star's bigger, badder brother. This is the really big end. Shooting stars are common, things like this are not so common. So that in itself was kind of startling. Got people's attention. People across the city, in the minutes after this, wandered out and saw this great smoke trail through the sky. And they were filming things on their phone. Before I start playing this video, I should put a little note of caution here. I don't speak Russian, which means I cannot vouch for the cleanliness of the dialogue that you're about to hear. If there's anybody in the audience who speaks Russian, please don't be offended if there's something in here that there shouldn't be, but I don't know what they're saying. But this is a few minutes after this great explosion happened in the sky. If you look up at the top of the picture here, you've got a bit of a smoke train in the sky. People are just stepping out of the building to see what happened. And this is what they see. That noise, that loud noise, is the shock wave from the explosion. Several minutes later, look at the windows, look at the cars. Hear the gunshots. Not gunshots, that's the echo from the explosion, the shockwave. It's a little surprise. But look at the windows of the building here. Every one of them smashed by that shockwave. It gives you a sense of the power, the violence of this explosion. That's enough Russian, I think. This great explosion was unusual in that it happened so near a city. And the result of this was that that shockwave that you heard there resulted in the injury of about 1,500 people. Very fortunately, there were no fatalities. I mean, if you see all the windows being smashed like that, falling glass, it's really remarkable nobody was killed. There were a couple of people who were severely injured, but they pulled through. Around 7,000 buildings in the city were badly damaged. Now, that's a very rough estimate because people are people. What I mean by that is that in the aftermath of this explosion, there were damaged buildings. And it turns out that some people took advantage of that. So one of the things you saw on the news, in true human nature style, one of the things that made huge news coverage was a warehouse that had been devastated, the roof had caved in. All on the international news. When the insurers came to look at this, it turned out that the roof was damaged shortly afterwards by hammers. But they were trying to take advantage to get a big insurance claim through. So that's why these numbers are a little hazy on the building damage sense. All of that damage was done by an object that was just 17 meters across. 17 meters from side to side, 17 meters from top to bottom. That's not very big. It's a bit bigger than this room, but it's smaller than your football pitch. It's quite a small thing. About 10,000 tons in mass, which is a lot more than me, but again, it's not actually a huge amount of material. But the reason it did so much damage was that when it hit the atmosphere, it was traveling at 30 kilometers every second. That's far quicker than your cars, right? It's carrying a huge amount of energy. Even though, as it plowed through the atmosphere slowed it down, aerobraking essentially. At the time it exploded, it was still traveling at 15 kilometers a second. The explosion happened, the explosion that caused that shockwave occurred 20 kilometers or so above the ground, which is why the sound took so long, took several minutes to reach the ground and cause all that damage. So if you think the explosion that smashed those windows happened 20 kilometers away, that's something like someone setting off a firecracker in Bondi and our windows blowing out here. That's really quite startling. In other words, that 17-meter lump of space rock detonated with 440 kilotons of energy, kilotons of TNT. That's equivalent to 30 times the energy of the bomb that was exploded over Hiroshima. It's truly astonishing, and this is something just 17 meters across. To give you an idea of the scale of it, here are a few other things that you might be familiar with in day-to-day life, and a few other examples of things that have hit the Earth. In the middle here, we have an estimate of what the thing that exploded over Chelyabinsk was like. 17 meters across. Smaller than a cruiser, smaller than some of the large ocean vessels we have cruising around. Smaller than a Boeing 747. Not a huge thing. Comparison, the thing that created Meteor Crater, or the Barringer Impact Crater, which I'll show you a photo of later on, was probably about 50 meters in diameter, more comparable to the size of a football pitch. The thing that we think exploded over Tunguska, also in Russia, 100 years ago, was maybe 100 meters across. The largest rock from space we found on the ground is the Hobart meteorite, and the meteorite we have left is 2.7 meters across, and I believe is actually a place of worship for a local tribe. This random lump of metal sat in the middle of nowhere. It's quite remarkable. But these are rocks from space. Thanks to us having this exquisite information from all those dashboard cameras from people driving around, we were able to go one step further in this case. So because we had people looking from here and other people from way over here, they could triangulate the path of this object through the sky. Different people looking from different angles. And if you put all that information together, you can work out exactly what path the object was following as it hit the atmosphere, which means you can work out where it came from. And this is what scientists have done here. So in the middle here you have the Sun, have the orbit of the planet Venus, the orbit of the Earth, and the orbit of Mars. And here, in yellow, is the orbit of the thing that hit the Russian city of Chelyabinsk. It's more eccentric, more egg-shaped than the orbits of the planets. Goes out into this region we call the asteroid belt that I'll tell you a bit more about in a little bit. But the thing is, the Earth's going around the Sun once per year, going like a car around a racecourse. The Chelyabinsk impactor was also moving around this orbit, and they've probably crossed one another's orbits many, many times. And in the past, it just so happened that when the Earth was here, the impactor was nowhere near the crossing point and nothing happened. When the impactor was here, the Earth was nowhere near the crossing point, nothing happened. Eventually, they just happened to reach the crossing point together, and the thing hit the atmosphere and blew up. The story, though, goes back further than that. The story of the rocks from space, the things that are hitting us, is actually the final act in the story of the formation of the Earth itself. So what I'm going to tell you about now for the next few minutes is a kind of fairy story. It's our best story of how we think that planets come to be. Now, it's a good point to say something quite interesting about science. We live in this world which is infinitely complex, which is incredibly beautiful. And science is our way of understanding that world around us. And science is a very narrative thing. We make stories. We come up with stories which we call theories. And the thing that differentiates the stories that we tell in science from stories that you tell in fiction is that we use those stories to make predictions. We can test those stories. But they're just our best explanation based on the evidence we have today. What that means is that as a scientist, I have my theories about how things work. In this case, a theory about how planets form. Every observation we make to test that can never prove it. All it can do is disprove it. So let's say I have a really simple theory. I have a coin. And I have a theory that when I flip this coin and it lands, it will either be heads or tails. So I flip the coin. We get a head or a tail. That hasn't proved the theory. All that's shown is that you can get a head or a tail when you flip a coin. So I flip it again. The more often I flip that coin and it lands a head or a tail, the more strongly the evidence supports my theory, the more it seems to fit. Let's say I've flipped it 1,000,000 times now. We really think this theory is going somewhere. It's a really good one. There is an infinitesimally small chance with a coin. If you flip it and it lands just right, it will land on its edge and balance. It's not going to happen. It's so immeasurably unlikely, but it could do. If my theory only says that a coin can land heads or tails, I could toss a coin 10,000,000 times, each observation supporting the theory. All I need is it to land on edge once, and the theory is disproven, because that's not a head or a tail. And that's the way science works. So what I'm telling you here is just our current best theory for planet formation. It's one that's so far been supported by the evidence we've got. We've discovered things that have shot down previous versions of the theory, and we've had to go back and improve our stories. But the important point I want to get across, because I think it's quite often not put across in the media very well, and quite often my fellow scientists don't portray it very well, is that science is an ongoing process, and that a theory is not a fact. A theory is just our best current explanation. That doesn't mean it's a fiction. It's the best thing we've got at the moment to explain the way the world is. And so this is our best fairy tale for how the planet's formed. And where this fairy tale begins is in large clouds of gas and dust that float through our galaxy. Our galaxy is huge. The sun, which is in one of the outer suburbs, lies a huge distance from the middle of our galaxy. Our galaxy is a city of stars. It's probably got 400,000 million stars in, floating around in a kind of spiral pattern. And in among the spiral pattern, there's not just stars and planets, but there's gas and dust. And at some locations, the gas and dust gradually drifts together and forms these huge clouds. And they can be really big. They can be so big that light would take 100 years to cross from one side to the other. Except there's so much dust it can't. It gets absorbed and blocked. They're really dark. If those clouds start to collapse, something gives them a nudge, they can start to collapse under their own gravity. And the more they collapse, the stronger gravity pulls them together, and they collapse and gradually form clusters of stars. And what you're seeing here with this incredible photo of the Orion Nebula is a cluster of stars that recently formed out of one of these dark clouds. So across the entire region here, you've got gas and dust. And it would normally be dark. It will block the light from behind it out. But that gas and dust has been collapsing, forming baby stars. And in the middle here, a young cluster of stars formed only in the last 1,000,000 years or so. And when stars are born, they throw out lots of light, lots of energy, and also have this thing called a stellar wind. They throw material off into space. And that acts like a wind and blows away from them. So the young cluster of stars forms in the middle of this black cloud and begins to blow the material away from around them. It clears a bubble in the middle of the cloud. The bubble gets bigger and bigger, and what you're seeing here is the bubble's now broken through the surface, and you're looking into the bubble. So you're seeing in 3 dimensions something like that, like my hands cupped together. In the middle here, you've got the stars, and here's the bubble they've blown. A new cluster of stars clearing the gas and dust away. Around those stars as they form, material is continually falling into them. They're growing bigger and bigger. They're drawing material in from the gas and dust around them. But that material's moving a little bit, so it'll be coming in with a bit of spin. And what happens then is something called the conservation of angular momentum. It's the same thing you see if you see a dancer pirouetting, pulling their arms in and spinning quicker and quicker. As you get closer to the center, you spin faster. But the problem is, if you're spinning really quickly, you can't fall into the middle anymore. Have you ever seen somebody make a pizza base, a professional in a restaurant? They get a big round lump of dough, spin it round really quickly, and miraculously a ball becomes a flat disc. Same thing happens here. You spin a blob of gas around really quickly, and it falls down into a disc. So these youthful stars, these protostars, are surrounded by disks of material, very thin disks stretching out with lots of stuff in there. And that disk is dust and gas. And the disk's got friction, so all the bits in the disk rub against their neighbours, so they're going at about the same speed, which means that collisions between one bit of dust and another are very, very slow. And if you throw dust grains together slowly enough, there's a chance they'll stick together. If you stick two small dust grains together, you get a bigger dust grain. That's now more likely to run into others and grab them as well. So gradually, over periods of tens of thousands, hundreds of thousands of years, your little dust grains grow bigger and bigger, until eventually you end up with a really big dust grain. We're stood on one, we call it the Earth. This is how planets form. When you're far enough from the star, the temperature's cold enough that water, instead of being a gas, instead of being a vapor, freezes out to be ice. And the universe is full of water, there's loads of it. So beyond a certain distance from the star, suddenly there's a lot more dust around because there's a lot of ice around as well, which means that the dust can grow into big things quicker. That's what happened with Jupiter and Saturn. They were far enough out that there was lots of water around. They grew bigger and bigger until they got big enough that their gravity could start sucking in the gas from the cloud around them. Loads of gas, so they suddenly grew these huge atmospheres, really inflated and became the giant planets we see. The reason the Earth didn't do that, however, is that this disk of material around the star doesn't last forever. Eventually the star turns on, and just as we saw the stars clear the bubble in that nebula, they also clear away the remains of the disk, and most of the material that's left that hasn't been soaked up into planets is removed. And the gas is really quickly removed, and you're left over with a few things left over, a lot of rubble, essentially. Sounds like a fairy tale, but we have evidence. This is photographs from the Hubble Space Telescope, looking in at that Orion Nebula I showed you before. And what you're seeing here, silhouetted against the bright background of that cavity that you saw, are stars with disks of material around them, where planets are forming today, as we speak. Each of these is what we call a protoplanetary disk, or a propylid. Now, those stars in the middle that are really energetically blowing things away are also blowing away the disks around these stars where planets are forming, which is why you see some of them have tails. Just like the comet you've got on the wall at the back. Material is being blown away, over there, back left as I'm looking at it. Beautiful comet. Comets shed material which is blown away by the solar wind, you get a beautiful tail. Here you've got a disk of material around a small star being blown away by the nearby stars, and again you get a tail. Very different scale, but very similar process. So each of these is a location where planets are forming as we speak. Eventually, the star turns on and begins to clear the material away, and you're left with a planetary system, a baby planetary system. But you're also left with a lot of debris. You're left with the big lumps of rock that haven't yet had time to plow into one another and grow to become planets. And that's the stuff that's still hitting the Earth. It's the final stages of the solar system being cleaned up. That's what's happening, and that's where the rocks from space come from. Now, these are just some examples of bits of rubble from our own solar system. One of the really cool things about the last 20 years or so is we've finally got sufficiently good at space travel that we can send spacecraft to all the different lumps of debris in the solar system. It's very expensive, so we only send a few of them, but we learn a huge amount. And what you're seeing here is the variety of debris left over. It's not complete. We've seen some more objects more recently. But an object here, for example, is an asteroid called Ida. It's shaped like a potato. It's about 60 kilometers long, about 25 wide. And it's got a little moon called Dactyl that we discovered when we went nearby. We've got big objects, little objects, really tiny ones. We've got icy objects, which are the comets. The Japanese have even landed on one of these things with a mission called Hayabusa. Went up to one of these asteroids, an asteroid called Itokawa, which is only a couple of kilometers across, rested down on the surface, took a sample, and returned that sample to Earth. That's how awesome some of the space missions we're doing today are. And these are lumps of debris left over from that planet formation process. Now, in the solar system today, 4,500 million years on from the story I've just told you, a lot of that debris has been removed, and the great majority of the leftovers are trapped in a couple of reservoirs, stored in cold storage. And we have several different reservoirs in our solar system that we're fairly confident are there, we understand how they're formed. The first of them is the one you're probably most familiar with, that you'll have heard of before, the asteroid belt. Now, this is a fabulous artist's impression. I love to show this. It's about as factually wrong as it could be, but it gives you a really good idea of how things work. A real image of this, instead, looks something like this. Not quite as pretty, but a lot more science here. Every dot on here is a bit of debris left over from the formation of the planets. There are probably about 600,000 dots on here at the minute, and more are being discovered all the time. For scale, here is the planet Jupiter, which orbits the Sun 5 times further from the Sun than the Earth is. The Earth is about here, buried in the middle of all these red dots. You've got Mercury, Venus, Earth, and Mars. This green donut is the asteroid belt. 600,000 or so lumps of rock, a kilometre or bigger across. Fairly stable, held in cold storage, left over from the formation of the solar system. The biggest of them series is of the order of 1,000 kilometres across, smaller than our moon, but big enough that gravity draws it into a spherical shape, and we call it a dwarf planet. The smallest things in the asteroid belt are probably meters across, and there are probably millions of them, but they're too small and hard for us to spot as of yet. Just for reference, you can see the 2 clouds of blue objects here on Jupiter's orbit. They're called the Jovian Trojans, and I'm just going to give you them as a reference point for the scale a little bit later on. They're moving Jupiter's orbit 5 times further from the Sun than we are, and we think there are probably about 1 million of them. Again, debris left over from the solar system's formation. This, I'll apologise by the way this screen will go bright white and give you some info text in a minute, but this is how objects move around the Sun. So in the middle you have Mercury whizzing around really quickly. The further you are from the Sun, the slower you move. So the Earth goes around every 365 days. Jupiter goes around every 12 years, and I'll sneak in at the top here shortly. The reason there's a red blob following the Earth is because it's easier to find things nearby than to spot things further away. The nearer something is, the easier it is to spot, so we have a bias and it's easy to find things nearby. But all these green dots in here are the main belt asteroids, and they stay typically fairly well constrained to this region between the orbits of Mars and Jupiter. And they're our first reservoir of material. We think in actuality, once we find them all, we're probably talking 1 million objects at least of a kilometre or so in diameter. Fewer the bigger you go, but still plenty there. And that's the leftovers from when the planets formed. Let's move further out, and this is where the scale comes in handy. This is the outer solar system. The 2 clouds of bluish things in here are the Jupiter Trojans that I just mentioned, 5 times further from the Sun than the Earth is. Here you've got the orbit of Saturn, 9 times further from the Sun than the Earth. Uranus, 18 times further away, and Neptune, 30 times further away. Now, things out here are much further away from the Sun, so they're harder to spot. They're much fainter. They're really difficult to see. That's why we see fewer things out here. But what we found in the last 20 years or so is that the space beyond Neptune is also full of debris. In fact, probably more debris than there is in the asteroid belt. We think there are probably at least 10 million and maybe even 100 million objects beyond the orbit of Neptune in a belt, just like the asteroid belt, but these objects are icy rather than rocky. There's lots of them. Again, they're the leftovers from planet formation, but these ones are so far from the Sun that they were beyond the ice line. They were far enough from the Sun that the water could condense to ice, so there was more material, so we have more of them, and they've got a lot of ice on them. But we have all these objects out here. When we get more observations, we'll probably fill in these gaps down here and up here. But the reason we see those gaps at the minute is nothing to do with how these objects are spread across the sky, but rather with how we discover them. These objects are very tiny, very faint. They look like stars, very faint star-like points, and we detect them by seeing them move against the background stars. If you want to look for very faint star-like points, you want to look at a part of the sky where there aren't many stars. The more stars there are in where you're looking, the harder it is to spot one of them moving. The direction down here is the direction towards the very middle of our galaxy, looking towards the most highly built up part of our stellar system, essentially. If you look in that direction, there are so many stars you just wouldn't find anything. Doesn't mean there are no objects there. All it means is that we can't see them. And so as time goes on, things move around the sun, we'll fill in the disk here. And we'll get a very good picture of that. But let's move out again. Let's talk about the Oort cloud. Now this is really cool. This is a comet called Comet Mcnaught that was visible, incredibly spectacular from Australia back in 2007. And Comet Mcnaught goes around the sun on an orbit that would take hundreds of thousands of years to complete. Goes a huge distance from the sun. But these comets, these long period comets that go around with periods tens of thousands, millions of years, are destroyed very easily. They're thrown away, they crash into things, they fall apart. So they must be replenished from somewhere. So back in the 1950s, a couple of astronomers called Mcnaught and N. Sopik independently looked at the data of all these comets that we've discovered in the past and say, hang on, there has to be a source for all these comets somewhere. They can't just be wasting away to nothingness because they get removed so efficiently they've got to be replenished from somewhere. And so we have to work out where they come from. Based on just a few tens of comets, they said, in order to explain this, the best fairy tale, the best story we can come up with is that there is a vast cloud of comets, 10,000 million, give or take, stretching out halfway to the nearest star. To put that in perspective with this artist's impression, everything we've talked about earlier, every figure that you've seen, is in an area in the middle here smaller than the dot of that laser pointer. The solar system as we know it's in there. Some of these objects are 20,000 times, 50,000 times further from the sun than the Earth is, held in cold storage. But once again, they're the remnants of planet formation. And they're the source of the long period comets. And I'll come on to the long period comets in a moment. But this is our third reservoir. This contains far more material than the asteroid belt and the trans-Neptunian region combined. But to give you an idea how big space is, remember 10,000 million objects, but space is so big that on average, they're further apart from one another than the Earth is from the planet Uranus. They're probably more than 1 billion kilometers distant from one another. Space is really big. But there are stable reservoirs. Those are the objects that, if you came back in 1,000 million years, they'd probably mainly still be here. We also have unstable objects, and these are the ones that are of interest for us in terms of protecting our own hides, in terms of rocks from space. Now this is a very artistic photograph of a meteor shower called the Leonids. Helpfully, people have drawn the lines of the constellation on here, but this is the constellation Leo, the lion. This is the head of the lion, this is the body of the lion here, the front leg and the back leg, so the lion's laying crouched down. Every streak of light you see on here is a shooting star. Shooting stars are unstable objects. They're objects the size of grains of dust, grains of sand, hitting the Earth's atmosphere. In the case of the Leonids, this meteor shower at 72 kilometers per second and burning up in the atmosphere. The reason they appear to spread out from a point in the head of the lion is that they're all traveling towards you. If you stood on a bridge above a motorway, above a highway, you see the road, you know it's parallel because the cars don't crash into one another. But from where you're stood, the sides of the road seem to converge into the distance to a point. It's exactly the same thing here. These things are all traveling parallel, but as they're coming towards you, they're spread out. That's why we see them spreading out on the sky. Now, these are really interesting in their own right, but because they burn up in the atmosphere, they don't hit the ground, they don't reach the ground, they don't really cause us any problems. The things that do cause us problems are the bigger objects. And again, there's a few different types. The first I'll talk about are the near-Earth asteroids. This is a nice artist's impression of a typical near-Earth asteroid. We've now zoomed in into the middle region of that plot of the solar system I showed you with the green donut, and we're looking at the red dots. The red dots are the near-Earth asteroids. Each one of these is an object, maybe some meters across, maybe kilometers across. The biggest is an object called Ganymede, 32 kilometers from side to side. If that hit the Earth, it would dig a hole 600 kilometers across and probably about 100 kilometers deep, and we'd probably not be here anymore. Fortunately, it's not coming anywhere near the Earth, so we don't have to worry, but that's the biggest of them at the minute. These objects are the daughters of the asteroid belt. In the asteroid belt, most of the material there has been there since the formation of the solar system and will be there if you come back in 1,000 million years. But because you've got a lot of lumps of rock there, occasionally they'll crash into one another. You'll get a collision. And when you have a collision, the fragments shatter off into all different directions in space, and some of them will be thrown so that they start to cross the orbit of Mars. They become a near-Earth asteroid, and once they're there, things are unstable. They get pushed around by the planets, nudged back and forth. Like a giant game of planetary billiards, They get flung through the solar system until eventually they're thrown away. Typically, an object in this region, a near-Earth asteroid, will only last about 1 million years before it hits a planet, hits the sun, falls apart, or is thrown out of the solar system entirely. But they're continually replenished by new material created by collisions within the asteroid belt. A good analogy is to think about the asteroid belt as a reservoir up in the mountains. Reservoirs are full of water that's been there quite a long time, especially when we've had nice rainy winters. And if you come back tomorrow or next week, the water you see in the reservoir will probably be the same drops of water that were there today. They're not going anywhere. Some will have evaporated, might have a tiny little bit more in there because it's rained, but the bulk of the water will be the same. Out of the reservoir, you might have a trickle of water that goes on to become a stream. If you stand next to the stream today and look at the water that's passing by you will flow off to the sea. If you come back tomorrow, the river will probably be about the same level. You'll have about the same amount of water in it. But the individual drops of water you see today will be different to the ones you see tomorrow. Because the ones you saw today will have flowed out to sea, new ones will have come along to replace them. The near-Earth asteroids are like the river. The reservoir is the asteroid belt. We think there are 1 million, give or take, asteroids in the asteroid belt bigger than 1 kilometre across. There are probably just a couple of thousand of near-Earth asteroids of that size, but they're continually being topped up. And that's our first threatening population. The second are the long-period comets, and I've already really described what these are. These are dirty snowballs. Some as big as 10 kilometres across, most smaller than that are flung in from the Oort cloud, that vast cloud of comets halfway to the nearest star, and as they swing past the sun, the ice on them begins to boil off, carrying with it dust and producing a glorious tail like this. The wind from the sun blowing outward pushes that material away, you get the tail. A cometary nucleus like Comet Mcnaught might be 5 kilometres across. The tail that it spawns can be so big that it will stretch from the sun to Mars. It can be 300 million kilometres in length from a tiny 5-kilometre dirty snowball. But there's loads of these. We know several hundred over the past few decades as we've got better at finding them. And they're the daughter population from the Oort cloud. And they move on really extreme orbits. So on this very old picture, back when people thought Pluto was a planet, I mean, again, we get things wrong in science all the time. Pluto definitely isn't a planet. Different discussion for later on in the questions, but really they got it right this time. We've got Jupiter, Saturn, Uranus, and Neptune, planets, moving on fairly circular orbits. These are the orbits of long-period comets. Comet Halley is actually a fairly short-period comet. It comes around every 76 years or so. At its furthest from the sun, it's just beyond Neptune. Comet West was spectacular in, I think, 1976, before most of us in this room were born, was really spectacular and bright. Comet Hale-Bopp was incredible in 1995-96, will be back in about 2,500 years. Comet Hyakutake was also great in 96, back in 20,000 years. Comet Kohoutek was frankly not very good in 1973, but people thought it would be the best comet ever. That'll be back in about 1 million years, so we probably won't be hanging around for that one. But these things are continually being slung in from the Oort cloud, fresh material all the time. Our third population are the short-period comets, like this jellyfish-looking object here. This is a real photo. This is a comet called Comet Holmes. Now, I've already told you about 2 populations of unstable objects and talked about 2 reservoirs from which they come. There's only 1 reservoir left. And we've got 1 type of unstable object left. We've got the short-period comets. These are dirty snowballs again. But instead of going around every 10,000 years, every 100,000 years, these things come back as regular as clockwork, with periods of 5 years, 7 years, 3 years. Comet Encke, the shortest period known, 3.3 years. It always stays so close to the sun that we can now observe it all the way around its orbit. Watch it 24/7, 365 days of the year. And we know 200 or 300 of these. Now, we said the long-period comets come from the Oort cloud. The asteroids, the near-Earth asteroids, come from the asteroid belt. We've got 1 reservoir left, the trans-Neptunian objects. And that's where we think that the short-period comets come from. But there's a problem. The trans-Neptunian objects are out beyond Neptune. The short-period comets are in near the Earth, closer than Jupiter. If this story's true, there must be a population of objects transitioning from the trans-Neptunian objects to the short-period comets. If I was giving this talk in the 1970s, that's as far as I could have taken it. But in 1977, these people discovered an object called Chiron. It's 150 kilometers across, and it's orbiting between Saturn and Uranus, and it's unstable. Within the next 3 million years, this was my PhD work, one of the objects I looked at. Within the next 3 million years, there's a 30% chance that Chiron, a 150-kilometer diameter cometary nucleus, will become a short-period comet. And what you're seeing is these objects we now call the centaurs are the transitory population. We now know tens of them, hundreds of them, depending on how you define it. And what's happening is just as the near-Earth asteroids were being replenished from the asteroid belt, the short-period comets, which also get removed, fall apart, are being replenished by the trans-Neptunian objects. You get collisions in the trans-Neptunian region, fragments fall across Neptune's orbit, you get planetary billiards, they bounce around, and about a third of them end up crossing Jupiter's orbit, being flung inwards, becoming short-period comets. That's what the centaurs are. And you can see them on our plot here. We've got the trans-Neptunian objects out here. 10 million at least, probably 100 million bigger than a kilometre across. You've got short-period comets in here clustered around the orbit of Jupiter. And in the space between, you have the centaurs, the daughters of the trans-Neptunian objects, the parents of the short-period comets. And that's the story of our solar system and where the debris come from. Why is that interesting to us from the point of view of a story of rocks from space? Well, that's where the debris comes from. That's where the rocks come from. Why we occasionally have things like this happen and species get wiped out. This really is an artist's impression. If that had happened, I wouldn't be here giving this talk. I'd be panicking and hiding and awaiting the arrival of the shockwave. But this is an artist's impression of what would happen if the Earth was hit by something 10 kilometers across. A typical, fairly large near-Earth asteroid or comet. You'd have material blasted out of the atmosphere. You'd have solid rocks blasted out of the atmosphere that could carry living bacteria to Mars. It's an idea called panspermia. Life may have been seeded to Mars. Life may have been delivered here from Mars in the past. Bacteria can survive these kind of impacts and fly through space, which is pretty cool. What can't survive these kind of impacts are people sat on the coastline here. You'd be hit by a shockwave that would demolish everything. You'd feel the effects of an earthquake bigger than a magnitude 9. I mean, the thing that hit in Tokyo a couple of years ago that caused all that horrible devastation would be a smaller earthquake than you'd feel if you were on the coastline near this. Then the tsunami would hit. You'd get a tidal wave kilometers tall, hitting you traveling faster than the speed of sound. You'd be very unhappy. Very briefly very unhappy as well. It would be a bad day, but fortunately these kind of impacts happen very infrequently. There's not much big stuff around. There's a lot more smaller stuff around. And we see the evidence of those impacts all over the place. This is a crater I'll come back to a little bit later on. This is Meteor Crater in Arizona, or more correctly, the Barringer Impact Crater, because the Barringer family purchased the land and they named the crater. It's a very recent impact. The far wall is 1.5 kilometers away, something like that. It's about 200 meters deep. It's a very small crater. This one is Manicouagan in Canada. You can see this on Google Earth. If you zoom in on the northeastern part of Canada, you don't have to go very far. This ring, the lake, is about 60 kilometers across. The outer wall, which is weathered down to almost nothing out here, is about 300 kilometers across. Now, this is a very old impact. It's almost weathered away to nothing, and it's only because it was so vast and catastrophic that the evidence remains now. But it's also a good indication of why impacts are not always a bad thing. This lake is dammed down here by the Canadian government, and it produces a huge amount of hydroelectric power. Catastrophic impact for the species that were around something like 2 billion years ago, or 200 million years ago, didn't help them out a lot, but now it's producing clean, green energy for the people of Canada and powers about half of the state of Quebec. That's the amount of energy it puts out. So impacts aren't purely a bad thing. This is the distribution as of a few years ago of the impacts across the Earth that we know of. And it tells you a hell of a lot, but most of what it tells you isn't about how the Earth itself is being hit. One of the things it shows you is how we do science. Again, if you want to find craters, you need to ask people for money to go on trips. Now, it's lovely to ask the government to say, I want to look for craters in the Maldives, please will you send me? But that's not going to work. So what typically happens is that scientists look for these things close to home. So if you look here in Scandinavia, you see a vast number of impact craters. That doesn't mean that Scandinavia is a bad place to go on holiday. It doesn't mean that the Norse god Thor has been angry and flung his hammer around. What it's telling you is that in Scandinavia there was a very active group of researchers looking for impact craters, and their funds were limited, so they looked locally, and where they looked they found things. See that areas like the Canadian Shield, you see lots of big impacts there. Again, that's not telling you that the Canadian Shield has a bullseye on it, but rather it's telling you that that's some of the oldest crusts on the Earth. And so that's had longer to build up evidence of impacts. It's just had longer to be hit, and so you have more impacts there. The reverse side of that coin can be seen on Iceland, and for a different reason in Brazil down here. In Brazil, you have a rainforest. You have less than there used to be, but you still have a lot of weathering. You need a really big crater, a really big hole in the ground, before that weathering won't remove evidence of it on short order. So simply, any big craters here will get worn away. But it's also very hard to look for craters when you've got a rainforest in the way. The trees obscure things. Iceland is some of the newest continental crust on the Earth. It just hasn't had the time to build up an impact record. And then we get to the oceans. So you've seen the movie. Good guy running away from bad guys who've forgotten how to shoot straight. Bullets flying everywhere. Good guy is perfectly safe but keeps running anyway. Jumps into a lake, and you see this slow motion shot of bullets hitting the water and then just floating down. And you think this is total gobbledygook. It must just be poetic license. It turns out, though, that one of the reasons that we see so few craters on the bottom of the ocean is that effect. It's that water is incredibly good at slowing things down. It's also partially the result of the fact that it's very hard to look through 6 kilometers of water to find out what's on the bottom of the ocean. But a really interesting experiment that was done by a young woman in the UK as part of her PhD was to fire small ball bearings at a target at a speed of 5 kilometers per second. And she put a layer of water over the top, and what she found was that you only need a layer of water about the thickness, about the size of the projectile, before you prevent that projectile leaving a mark on the surface of the solid material under the water. In other words, the movie's right. Bullets will stop when they hit water very quickly. Now, that doesn't mean that impacts on water would be less damaging. All it means is that you dig a crater out of the water rather than the land, and instead of having a big hole in the ground, you'd have a big hole in the water, which means you'd get tsunamis, you'd get really big problems. Still have problems, but millions of years down the line, there wouldn't be a scar telling you that there'd been an impact there. If we want to get a real feel for how often the Earth's been hit then, we look next door, we look at the moon. And the moon is smattered by impacts everywhere we look. There are new impacts and old impacts. Young impacts, like this one here, you can see the rays radiating from the impact site. That's a sign that this crater was formed very recently. The surface of the moon is exposed to space weathering, radiation from the sun, the solar wind, and that gradually causes it to fade, to turn dark. But it only affects about the top metre or 2 depth of the moon. Everything beneath that's protected by the rocks on top and stay quite bright. When you get an impact, something ploughs into the surface of the moon, digs material up and splashes it across the surface, digs the bright material up, throws it across the surface, and you get these ray craters. They will fade away to the darkness of the moon on periods of millions of years, so eventually the rays will disappear, so these have to be new. And the moon's been hit time and time again. You see craters inside craters on top of craters. It's incredible. Down to the smallest scale you can see here, there are craters, and if you could zoom in and see more, you'd see more. But it's not just the moon. This is awesome. This is a photograph of Victoria Crater on Mars, and I urge you to, if you're at all interested in this, try and find this photo at the full high resolution when you've got a really good monitor. So if you zoom in, at the top here, you can see the tracks left by one of the Mars rovers. You can see one of the Mars rovers itself. You can see the shadow cast by the little antenna on top of the rover. It's truly astonishing. If this camera was in orbit around the Earth, the US military wouldn't let you see the pictures. They're that high a resolution. This is only a couple of 100 meters. It's Mars, there's weathering, but you've got a crater, another one, another one. Craters are everywhere. The most famous case of craters, certainly for the general public, is the one at the Yucatan Peninsula in Mexico. So this is an artist's impression of what the Mexican Yucatan Peninsula would have looked like 64 million years ago. This is an artist's impression of what it would have looked like 65 million years ago. It's the most famous rock from space. It's this story that a giant rock helped to kill the dinosaurs and dug a huge hole, which we found, oil exploration, discovered a 300-kilometer crater buried beneath the Yucatan Peninsula. It's not quite the whole story, but certainly a big part of the death of the dinosaurs came down to this 10-kilometer impactor ploughing into the Earth, causing a nuclear winter, causing a firestorm, causing hellish, unimaginable conditions. But it's not a historical thing either. Impacts are happening today. So this is another photo of Meteor Crater, the Barringer Crater in Arizona. We think this was formed about 50,000 years ago. In other words, when this formed, our ancestors may well have been running around the plains in America. There may well have been people who witnessed this. Now, if they were close enough, they won't have become our ancestors, but the ones a bit further away may well have witnessed it and survived. This was something the size of a football pitch, 50 meters across, and it dug a hole that was about 1,400 meters across, 200 meters deep. It's in the middle of the desert, which is why it's so well preserved, but even so, another couple of 100,000 years ago, and this crater is small enough that most evidence will have gone. More recently, 1908, now this is an artist's impression, but there was the Tunguska Event. It's a favourite of conspiracy theorists everywhere who think it might have been an alien UFO with a nuclear-powered drive exploding. It's a fairy tale. It's not really a very good theory, but it's a good fairy tale. It's great fun. What we think really happened was that a 100-metre-sized fragment of a comet called Comet Encke that I mentioned earlier hit the Earth's atmosphere and blew up over Siberia. It's the biggest impact that we know of in recorded history. This is what it did. A huge area of trees about the size of Greater London was levelled. Vast area. A few reindeer died. Nobody was hurt because it hit, fortunately, in a very isolated part of Siberia. But the area of trees that was levelled was about 2,100 square kilometres. This explosion was 1,000 Hiroshimas. To put that into perspective, let's imagine that for some reason we don't like Auburn. So we blow the Tunguska impactor up above Auburn. If you were anywhere in that circle, you would have been knocked over like these trees. You'd probably have been killed. That's the kind of area that was levelled by the Tunguska impactor. If it hit Guildford and you were surfing in Bondi, you'd have been knocked off your board. If you're at the bottom of the Blue Mountains, you'd have been knocked off your feet. It's a big impact. But it's only a big impact from the point of view of a city. And most of the Earth is not city. It's wilderness. This just happened to hit Siberia. But impacts keep happening. This wasn't actually an impact, this was a near miss. But it was the first real photograph of a near miss. 1972. In the north of the US, people saw this. This is daylight. This is bright enough that random people were distracted by it and looked up. It wasn't just those who naturally look at the daylight sky, the nighttime sky. People saw it and got it in very old photographs. This was something the size of a house that hit the Earth's atmosphere but skipped back out again like skimming a stone on a lake. The closest it got to the ground was about 57 kilometers high. But people still heard a shock from it, a sonic boom across two of the American states. It was a big close encounter, but it was particularly noticeable because we got the photos. The most exciting for me though, prior to Chelyabinsk, was 2008, because this is a turning point. This was another small object, just 2 kilotons of TNT, probably just a few meters across, but this was the first time in recorded history that we discovered something prior to it hitting the Earth. We discovered a space rock, observed it, we said this is going to hit the Earth in a week's time, and it did. It's hard to explain how awesome that is, because it means that for the very first time, unlike the dinosaurs, we can now find things before they hit us, rather than realizing that they just did and then falling over, which means we're at a position where we can start doing something about it. But as we saw with the Chelyabinsk impact, we're not quite there yet. These things still catch us by surprise. And that's probably the biggest impact on Earth for the last 100 years. But it's not just the Earth that's been hit. This is just reminding you where the object came from. And with the knowledge we got earlier on in the talk, you can now see that this was a near-Earth asteroid, albeit a very small one, originated in the asteroid belt. The Earth's quite a small target, though. The biggest target in the solar system is Jupiter. And back in the early 1990s, people discovered this very peculiar object, a string of comets. It's comet Schumacher-Levy 9. And in 1992, this comet came really close to Jupiter, so close that Jupiter tore it apart, tore it into 20-something pieces. 2 years later, it looped away from Jupiter, looped back in, and one after the next, those pieces ploughed into Jupiter. 23 big impacts and a lot of little ones. The biggest of those fragments was probably only half a kilometre across, 500 metres across. The scars you can see here are the size of the Earth. And they lasted for over a year before dissipating. You could see them with the kind of telescopes you'll be using in a little while. They were that obvious. I was 16 at the time, local Astronomy Society member, and every night for a week in July we watched these scars appearing on Jupiter. Night by night there were more. It was absolutely astonishing. Really cool. And then it happened again. Smaller impact, 2009. Here's another one. And again, there's a guy in Western Australia called Andrew Wesley, who's an amateur astronomer with really good equipment. He keeps seeing things hit Jupiter. Tiny little flash there. That's an object exploding in Jupiter's atmosphere. Can't really see the scar there, But here's another one. Tiny little object hits, tiny little scar. Jupiter's continually being pummeled. It's the biggest target, so it gets hit the most often. The point from all that is that the Earth is going to be hit again, guaranteed. But what can we do about it? Well, first thing we can do, not very much yet, but the first thing that we can do is to try and look for the things and spot them beforehand. And that's what we did in 2008. This is just trying to illustrate what fraction of the objects we think are there that could threaten us we've discovered. For the objects bigger than a kilometre across for the near-Earth asteroids, we've discovered just over 90%. 9 out of the 10 blocks are filled. We're fairly complete. It becomes more worrying as we get to smaller sizes. 500 metres across to a kilometre, maybe only 50% of the near-Earth asteroids. And the smaller we go, the fewer we get. Tunguska would have fallen among this lot, less than 10%. But we're getting there, and the reassuring thing is that as time goes on, we're filling these blocks up. So let's say we find one of these objects that's going to hit the Earth. We work out that it's going to. What can we do? If you believe Bruce Willis and the wonderful people at Hollywood, you send a team of miners up there with a bomb, because it's easier to train miners to be astronauts than to train astronauts to plant a bomb. It makes sense. Send them up there, blow the asteroid up. It achieves something. It gets rid of Bruce Willis. It's up to you if that's a win or a loss, but it achieves that. But this is a really bad idea. You blow an asteroid up, and all the bits of the asteroid keep moving in the same direction. You've turned one impact into millions of impacts, or 100 impacts of big objects. You've turned a bullet into a shotgun blast. This is not what you do. Even if you really dislike Bruce Willis, you avoid doing this. There's cheaper ways of dealing with that. What we think he'd do instead is try and find these objects long enough in advance that we can nudge them. The longer in advance you find them, the gentler you have to push to change a hit into a miss. If it's a week away, you have to push really hard. You're not going to manage it. If it's a year away, you can push more gently. And this is just an artist's impression of one of the ways we could use sunlight to possibly make an asteroid miss the Earth that was going to hit. And we're actually starting to test this. This is an awesome image from 2005, a mission named Deep Impact. We sent a space probe up to a comet that comes nowhere near the Earth, so even if we nudge it, it still won't hit us, because we don't want to make that mistake. And we fired at that object a lump of metal, 370 kilograms of metal. We fired it into the comet at over 10 kilometers a second and watched what happened. And very little did. The comet was barely moved. It dug a bit of a hole, the thing just sank into the comet and disappeared. It was a bit of an anticlimax, actually. The reason that not much happened is that the comet is 7.7 kilometers by 4.9 kilometers across. In other words, the comet weighs 200,000 million times more than the impactor. It's like trying to stop a four-wheel drive Jeep by hitting it in the windscreen with a fly. Except a very, very tiny fly. It's not going to work, but it's the first step along the road. We want to find out what happens. And the only way is to start small. The next step along the road, if it gets funding, is a mission called Don Quixote. It's a European mission, European Space Agency. And they want to do deep impact again, but bigger, better, stronger, faster. They want to take a satellite and put it in orbit around an asteroid and follow the asteroid for a fairly long period of time, one of the near-Earth asteroids, and then hit it. And by following the asteroid really closely, we'll be able to measure the tiny, minuscule effect we have on the asteroid. We'll also be able to get a feel for how hard we can hit something before it falls apart, which is, given that we don't want to blow these things up, quite important to know. The long-term future is that if we discovered something today that was going to hit in 10 years' time, I don't know whether we'd be able to do it, but we've certainly now reached a point where we can start to think about doing something about it. And I think that's a really important thing to think about and a really good place to finish. We are, for the very first time that we're aware of, a species on this Earth that may be capable of seeing something that would end our life as a species and to do something about it. It would take governments to agree with one another, which is challenging, but might motivate them to do so. But we're finally getting to the stage where we could do that. Just before I take questions, I just want to give a very quick advert for 30 seconds of something cool happening next Wednesday night. Here's a photo of a previous occurrence. The planet Saturn, which you'll see this evening if it's still clear, which it is, we're getting nods. The planet Saturn is going to pass behind the moon next Wednesday evening at about 9 p.m. It'll disappear for an hour and then reappear. It's called an occultation. If you want to know more info, I'll pass this link on. This is an article I wrote in collaboration with the head of the Melbourne Planetarium, Dr. Tanya Hill, just describing what's going to happen where you can see it. So I wanted to flag that up for those of you either with the unaided eye to go out and look at, or if you've got telescopes or binoculars, you can watch the beautiful planet Saturn vanish behind the limb of the moon. So with that, I'll take any questions you have. Thank you very much for your attention. Cheers.